This lesson is on significant figures. What are they and why are they used? To get you thinking about significant figures, I want you to think about two different instruments that can be used to measure mass, a bathroom scale and an analytical balance. The precision of these obviously are not going to be the same. The bathroom scale is not very precise, cannot measure to a very small fraction of a unit of mass, whereas the analytical balance can measure to a very small unit of mass. But just because the analytical balance measures to a smaller unit of mass does not mean that it is infinitely precise. Every measuring tool has a limit to its precision. In other words, in every measurement, there is some degree of uncertainty. If I have an instrument that can measure to the tenth of a centimeter, then I don't know the hundredth of a centimeter. If I have something that measures to the hundredth of a centimeter, I don't know the thousandth of a centimeter, and so on. And of course, that can go on to an infinite amount of measurements. So no measurement is infinite. In other words, every measurement has a degree of uncertainty or a certain degree of imprecision. Let's get back to this bathroom scale. Let's say I stepped on this bathroom scale and I looked down at it and I said I weigh that particular weight. You probably wouldn't believe me, and you would have good reason to not believe me. To report a number greater than the degree of precision than the instrument can deliver is dishonest. And so if I look at the bathroom scale and I say it has that degree of precision, I am not being honest. And so we cannot report numbers with a greater degree of precision than we know. Likewise, we should not report numbers to a lesser degree of precision than I know. Let's say the bathroom scale can read to whole pounds, but I don't like 174, so I change that to 170 pounds. Again, that is dishonest. Every instrument has a certain degree of precision. Significant figures will help you indicate the degree of precision, how well you know a certain measurement. And again, to report it with more precision or less precision is dishonest. Again, to get you thinking about significant figures and measurement, let's say an aerial view of a crowd of people is estimated to be 460,000 people. In this measurement, only two of these digits are significant. All the rest of these are placeholders. In other words, these two numbers are believed to be measured and known. The rest of these are just placeholders. And so in significant figures, there's a lot of rules about zeros because sometimes zeros are actually measured. Sometimes zeros are just placeholders in very large estimated numbers, but also in very small numbers, zeros can be estimated. So if I want to measure a bristle width, and if I could magnify it so I could actually see it quite well, I might measure that to be 0.006 centimeters. I can see that it is less than the 1. I can see that it is less than the tenth, and so I can estimate it to be 0.06 centimeters. Well, again, here we have zeros that are just placeholders. That's actually not part of the measurement, but those zeros must be there to indicate where that 6 should be. Definition of significant figures. Significant figures are all the digits of a measurement that can be known precisely. That is, you can't argue with them. You can see the lines, you can see the indications on the measuring tool, plus a last digit that can be estimated. So it includes only digits that are actually measured. At least the significant figures are the only digits that are actually measured, and it indicates the precision. That is really the key reason we are using significant figures. It indicates the precision, how well you know that number. So let's think of a measurement. Let's say an object comes up to this point on a ruler. Okay, the measurement, we can see the ones place precisely on this ruler. So we know that that measurement is between 1 and 2. We can also see the tenths place on this ruler, and we can see that it is between the 0.9 and the 2.0. And so those two numbers are known precisely. We can see the ones place. We can see the tenths place. Nobody's going to argue that the first two digits are 1.9. But I can't leave it at 1.9 because I see that it's between 1.9 and 2.0. And so the last digit has to be estimated. And I put a 3 down, but if you put a 4 or 2, can't argue with that. The last digit is estimated, but it's much better to say 1.93 or 1.92 than just say, well, I don't know it for sure and write 1.9, because again, that would be dishonest, or just say it's 2, because that, again, does not indicate the degree of precision that you should be able to tell with this particular ruler. Give you a little more practice with this. If we think of, let's start with letter C, then do we know the ones place precisely? Yes, we can see it's between the 2 and the 3. Do we know the tenths place precisely? Yes, because we can see it's between the 2.9 and the 3.0. And again, the last one has to be estimated. And so you might estimate it at 8 or 7. And that again is okay, but it's better to say 2.98 than 3.0 or 3 or 2.9, something like that. If we go to letter B, here we can see the arrow seems to be pointing exactly at the 2. So should I leave it at just 2? The answer is no. Again, significant figures are all those you know precisely plus one additional estimated place. So for this number, we can see the ones place, so we know it's a 2. We can see the tenths place markers, so we know that it's exactly there. Plus, we can estimate one more place since it's exactly on that, not to the right, not to the left. We really need to say that this is 2.00 centimeters. In letter A, I would put 0.009. Again, that last one is estimated. Really might be a 0.08, 0.07. Depends on how you're going to estimate it. I put 0.09. That seems to be correct to me. But again, these first zeros are just placeholders. If we look at the second ruler, now we only know the ones place precisely. So again, significant figures, all those we know precisely. We can see the markers on the ruling instrument, and we have to estimate to the next place. So in this ruler, we can only estimate to the tenths place, and so I put 1.5 centimeters. Obviously, the second ruler is not as precise as the top ruler. The top ruler, we're carrying it out to the hundredths place of a centimeter. The bottom ruler only to a tenths place of a centimeter. So the rules for significant figures. First rule is all non-zero digits are significant. Significant means they're contributing to the meaning of the measurement. They're not merely placeholders. Any non-zero digit in a measurement is going to indicate some form of the measurement, so it's going to be significant. Otherwise, you wouldn't put it in there. So this one has 4 significant figures. All these digits are non-zero digits. This one has 7 significant figures. Again, all non-zero digits. This one has 5 significant figures. Again, all non-zero digits. All indicate a part of the measurement and are not merely placeholders. Zeros, there's lots of rules about zeros because again, zeros can sometimes be placeholders. Zeros between significant figures are significant. So according to rule 1, that's a non-zero digit, it's significant. That's a non-zero digit, it's significant. All these zeros are between significant figures, therefore they are significant. So that measurement has 5 significant figures. And a better way to think about this is if we're measuring grams and we have a measuring tool that can measure whole grams and it can measure a 10,000th of a gram, it must also be able to measure everything in between. Therefore, those aren't just placeholders, those are measured values. This one, again, if we know to that value, as large as that value and as small as that value, we must know everything between. So that one has 10 significant figures. This one here, these are the only zeros between significant figures. So given that number, we must assume that these are just placeholders and are not significant. So that one only has 4 significant figures. Again, these zeros are not between significant figures, so we have to assume that they are placeholders merely. Zeros in front of non-zero digits are not significant. They are merely placeholders. So all these zeros are what we call leading zeros. They're not significant. This zero is between significant figures. So that measurement has 3 significant figures. These leading zeros, again, are not significant. This zero is between non-zero digits, so it is significant. So that one has 6 significant figures. Leading zeros, again, not significant. So this one has 4 significant figures. And again, leading zeros indicate that whatever measurement this is, it's smaller than the ones, smaller than the tenths, smaller than the hundredths, so they're not measured values, and therefore they are placeholders. Zeros at the end of a number, which are to the right of a non-zero digit and a decimal place, are significant. So how do you tell if trailing zeros are significant or merely placeholders? If they are to the right of a non-zero digit and a decimal place, they are significant. So here we have a decimal and we have a non-zero digit. Therefore, these zeros, which are to the right of both of those, are significant. Leading zeros are not significant, so that one has 3 significant figures. Again, these zeros are to the right of a decimal and to the right of a non-zero digit. Next one, are these zeros significant? Yes, they are. They're to the right of a decimal and they're to the right of a non-zero digit. So these zeros at the end are significant, but these zeros are also significant because that makes them between significant figures. So this one has 6 significant figures. This one has 3 significant figures. We don't count this part as significant. That represents placeholders. And the last one, these last zeros, we must again assume that they are merely placeholders. They are not both to the right of a decimal and to the right of a non-zero digit. This zero is significant because it's between significant figures. Therefore, that measurement has 3 significant figures. Sometimes measurements are made where a trailing zero is actually part of the measurement. In other words, it is significant. So in this number here, 2,050,000, let's say we actually know that that is a measured value. We know that number to be precise, or it's measured to that particular value. But right now, since it's a trailing zero, it does not look significant. To avoid confusion whether a trailing zero is significant or not, you must convert to scientific notation. Scientific notation always takes the form as 1 significant figure to the left of the decimal, all the rest of your significant figures follow, and then it's times 10 to some particular exponent. And so for this one here, there are 4 significant figures. And so when I change to the scientific notation, I need to include all 4 of those significant figures. Again, these are the numbers, the digits, the places that are actually measured. And then I'm going to multiply it by 10 to an exponent. If it's greater than 1, the exponent is positive. I'm going to move the exponent from here, move it over 3, 6 places. So that is going to be times 10 to the 6th. On the next one, we've got 1,050,000. Now I want to make this zero significant. So I've got 5 significant figures. Again, I want to include all 5 of those significant figures. Decimal goes 1 place to the right of the first significant figure. All the rest of my significant figures follow. And then we're going to move the decimal 3, 6, 9 places. So that is times 10 to the 9th. When the number is less than 1, then we use a negative exponent when it's between 0 and 1. Here we have 4 significant figures. So we are going to include all 4 significant figures in the number. And then again, multiply by an exponent, this time times 10 to the negative 3rd. We're going to move the decimal to the right 3 places. And so that is going to be 2.030 times 10 to the minus 3rd. Next one, we've got 4 significant figures. We're going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 places to get it to the right of the first significant figure. So that then is going to become 3.405 times 10 to the minus 9th. Last rule for significant figures, Defined or exact quantities have an infinite number of significant figures. A defined quantity is an actual measurement like a mole or a dozen or a yard. Those are defined or exact quantities, and therefore they have an infinite number of significant figures. Also, things that are counted, like 5 students or 3 cars, these are exact numbers, and therefore they have an infinite number of significant figures. And that will end this lesson.